Hello everyone and welcome to MakeLearn 360. Alright, so in this video I'm going to teach you the area moment of inertia of a triangle from first principles. So over here you can see a triangle, and then you realize that there have been some portion of the triangle taken. So actually we are going to look at Ix. So Ix of this triangle is going to be integral of y squared dA. Okay, now basically for this triangle, if I take dA is more or less like taking an elemental strip, and this elemental strip is what I have highlighted. You would realize that in essence this elemental area is like a rectangle. So it has got area of a rectangle given by the length, which is the L, multiplied by the thickness, which we are calling dy. So we know that this the elemental area dA is what we have here. But if I put everything inside, I have y squared, I have L dy. But you realize that we need to actually make some adjustments here, because we are going to do with x. Therefore, we need to make sure that everything y here will go to x. So we are going to use the concept of similar triangles. Now, what is similar triangles? So think about it this way. Consider the whole of this structure here as one triangle. Okay, consider the whole of this as one triangle, and then consider this small triangle here. Okay, so that's what we are trying to say. From there we can write that L divided by B. Okay, we can write that L divided by B is actually the same as H minus Y divided by H. So think about it think about it this way. So we are saying that for similar triangles, corresponding sides are equal. So the length of this small triangle divided by the length of this big triangle should be the same as the height of this small triangle divided by the height of the bigger triangle. And that is all what we are trying to say here. Okay, so that's all what we are trying to say. Now that we have this, we can do some gymnastics and then have our way. So basically this is what we are going to do. From what we have, let's make L the subject, and let's see what will happen. If we make L the subject, what is going to happen? It's going to be L is equal to B multiplied by H minus Y divided by H. After doing this, then we go back and put this into this formula here. Then we can say that H is going to be L dy, but then what is L? So now we know that L is B H minus Y divided by H, and then we multiply this by dy. So the whole of this is like L. So we are just multiplying L by dy. Okay. So from here, we can now go back. Let's look at the equation. You see that, what did we say? We said that integral, right? So let's go back. So it means that we can write Ix is actually integral of y squared. In fact, it's actually y squared dA. But then dA is what we have. So this is what I'm trying to say. Ix is integral of y squared dA. Now we know dA. So it's going to be y squared b h minus y divided by h dy. Okay. So this is what we have here. So then what are we going to do now? This is going to be pretty much simple. At this juncture, we are just going to separate the constants from the variables and then we integrate. So now let's try and do that quickly. So we are going to actually factorize b out of h out. So b over h will come out. Then we are going to do integral of y squared multiplied by h minus y dy. And when we do this, we get b divided by h integral of h y squared minus y cubed dy. So I've just multiplied through by h squared. So ix is going to be b divided by h, then multiply by h. I have got y squared. So basically I just have to integrate. Now watch this. We are dealing with integral with respect to y. So the h will not change, but the y is going to change, and then it's going to be y cubed divided by 3. Similarly, to integrate the y cube is going to be y4 divided by 4. All right, and all of them we are going to take the integral from 0 to h. Don't forget that we are looking at the integral in this sense. Okay, so basically we will just have to sum up all the small rectangles. That's what we are trying to say, all the way in this h direction. Okay, so now let's simplify what we have here. So we can say that ix from here is going to be b divided by h multiplied by if you put h and 0, of course the 0 will go, so we'll be left with h cubed on 3 minus h4 on 4. So what do we have then? So we are going to get that is, so b and then h will cancel one of the h, so bh cubed over 3 minus, again one of the h will cancel, then we get bh cubed over 4. So interestingly, we are basically going to get bh cubed over 12. You can do the algebra and you end up with this. So all that we are trying to say is that if I have a triangle, then the the mass moment of the area moment of inertia about the x-axis, in this case about this axis, is actually given by bh cubed over 12. So that's all what we were trying to say. Now let's do something important here, and let's try to find about the centroid. All right, so now that we have the centroid, now that we have the moment of area about the x-axis, let's try and find the moment of area about the centroidal axis. So it is a known fact that whenever I have a triangle, the centroid of that triangle will always be at a distance 1/3 from the base. Okay, so if this is like h, the centroid will always be at 1/3 of h, and so that is what has been depicted here. Okay, there is this formula which we call Ixs is given by ICG plus AD squared. Now, interestingly, what we are actually calling AD squared is nothing but the area multiplied by the distance between. So this is actually what we call the parallel axis theorem. So the parallel axis theorem, which is saying that we can find the area moment of inertia of any axis which is parallel to some arbitrary axis. So if you want to find the centroidal axis, the moment of area about the centroidal axis, then it's going to be IXS minus AD squared. And which is also saying that we just solve for ISS for a triangle. We said is BH cubed over 12. So minus the area of a triangle is 1/2 base times height, and then D squared is 1/3 of H, which is actually the distance between the x-axis and then the centroidal s-axis. Okay, so that's like the parallel axis, the distance. So multiply by H. Now if I do this, what am I getting? ICG. So ICG is nothing but BH cubed over 12 minus BH squared divided by 6. So let's try and simplify this. We've got 12 as LCM. So BH cubed I think there's a mistake that we did. It's actually squared, the distance squared. So this one is actually going to be 1/2 BH multiplied by H squared divided by 9, because the square of 3 is actually going to be 9. So it's actually going to be ICG equals BH cubed over 12 minus 1/2. Okay, so BH cubed 2 into 9 is 18. Okay, so it's going to be something like this. LCM of 12 and 18 is 36. So we've got 12 into 3, 12 into 36 is 3. So BH cubed minus 18 into 36 is 2. So in fact, our ICG is nothing but BH cubed over 36. And what this actually means in practice is that whenever you have a triangular area, then this the area moment of inertia about the x-axis will be BH cubed over 12, this one. However, about the centroidal axis is actually given by BH cubed over 36. All right. So thank you very much for watching.